then the idea is to look at some rough initial scale bounds, initial parameter bounds, and then just go ahead and calculate what would the value be if I evaluated beta hat at each one of these values. Okay. And then I want to do a pairwise comparison. So I do pairwise comparisons because I can't, after all, figure out how close this deviation is. I don't know what beta star is, right? So all I know is what I got when I calculated beta hat at each of these intervals, and I can compare the beta hats that I get from different points. So what I want to do is I want to check for each sigma. I want to check whether it's in a good set or not. And it's in a good set if whenever I do a pairwise comparison of something to the right side, then these things are close to each other. And the reason why this makes sense is that if I were looking at sigma j, let's see, over here, all right, so then it should be in the good set. Because when I do a pairwise comparison with anything to the right, I know that these are both going to be close to the true beta star. So the difference has to be close as this. All right, so with high probability, by my earlier results, everything here is in the good set. Everything that I do pairwise comparisons with will be in the good set. Okay, so my estimator will come as the minimum of all the sigmas in the good set. So with high probability, the minimum is going to be at least here. It might be over here. Okay, so then you ask, well, what happens if someone accidentally passed the test, right? Because I don't actually have any guarantee of how this estimator is behaving if my sigma is lower than sigma star. But I do know that if sigma j accidentally passed the test, then it has to be close to a beta that's over here, right? Because I'm comparing with everything to the right. And so in particular, it should actually be close to beta hat sub sigma star, which is exactly what I want. So Levsky's method will say that whatever solution I get, I'm not sure if my sigma that is output will actually be close to sigma star, but I do know that the quality of my estimator is at least, is comparable to the quality of the optimal estimator. Okay, so this is a nice little trick, and it actually, I mean, so you can show, it's not too hard to show the result here, and it's just that the output of Levsky's method is basically nearly optimal. So I think what ends up happening is there's an extra factor of 6 that comes, and your high probability bound is going to be a slightly lower probability, but that probability is still going to 1 as the problem parameter scale. Yeah. This is the way that Levsky's method usually works. Yeah. Yeah, I mean, because you need to compare it with something, and you would really like to compare it with beta star, but you don't know beta star. So all you can do is look at 2 different estimators and compare them somehow, right? Mm-hmm.
Because your conditionless works.
Mm-hmm. Right, right.
If you got your sigma, let's say your sigma max is smaller than sigma star,
Mm-hmm.
maybe there's a problem.
Right. So basically you want some interval that will contain sigma star, and then you do it geometrically. Yeah. Yeah. Okay. Great. So then this thing works. All right. So then there's some more you can say, but I think it gets a little bit technical statistically. But so in this Levsky's method procedure, right? I'm saying just use a Huber loss. And you might want to say, well, what if I, want to actually optimize some non-convex thing? Well, as I said, this is my most recent work. So since then, I learned some more about robust statistics. And I realized that you actually don't need to do this 2-step procedure where you get an initial point and then you iterate all the way to local optimum. So actually, in classical robust statistics, there are these notions of 1-step estimators. And this is kind of a nasty thing. But, okay, so a 1-step estimator in robust statistics is an answer to how you would actually get a good solution to your non-convex problem. And there they just care about having the same asymptotic variance. And so the idea is that if you happen to have a good initial point that was pretty close to beta star, then you can get the same asymptotic variance, not necessarily by taking a large number of gradient steps to convergence, but by just taking 1 step. So these are called 1-step estimators, and this is something that Peter Bickel worked on in the 70s. And so the idea is that you get your initial point, let's say from solving this Huber with Levsky method that I told you about, and maybe that's a really inefficient, not computationally, but the variance is really big because I want to solve a non-convex problem. Then what you should really do is you should do 1 step of Newton's method, where here what do you plug in? Well, this is like L prime, right? Because Newton's method says that I want to look at the essentially a Hessian term and then the derivative term, and that's what comes in here. This is also sort of a timely problem to look at because very recently people have been looking at what they call inference for the lasso. So if you want to construct confidence intervals for what comes out of lasso, this is a completely different line of work. But these sorts of one-step estimators and the type of analysis also show up there. Okay, so we can improve efficiency is the basic idea. Okay, all right, so I'll wrap up now. So what have I shown in all of this? Well, the first part of this was about this kind of restricted strong convexity condition and how some notion of it can be adapted to non-convex problems to show that local optima of these types of M-estimators are well behaved. And then when I moved to the case of robust regression, the problem was that in robust regression, I might want to look at a loss function where the non-convexity is not going away, even if I extend n to infinity. There are still going to be local optima that are further away from beta star, but hopefully I can get some good basin of attraction and some nice property of certain local optima, and that's what I was able to do here. And then I guess if you just want to focus on the robust regression message, then the message is that here is a high-dimensional perspective under which a bounded derivative loss function is a good thing to look at. So in low dimensions, people were looking at it from the point of view of influence functions and bounding this functional derivative. And now we can say that, in fact, bounded derivative loss functions are also good from the point of view of high-dimensional statistics theory. And then I think this other nice thing was this idea of Levsky's method, which is just useful in general when you want to adapt to something. So the nice thing is, like, I mean, really, if you have two parameters, then you just grid out one of them, and then you do these comparisons, and you can find the optimal solution. So thanks very much.
Almost perfect ending in terms of time. We have time 5 minutes, and of course, following around maybe around so you can present on.
Yeah.
I've always wondered, you said the Levsky method works only in one dimension, but there is some issue when you want to go to higher dimension. So the question is, why do you want to go to higher dimension? Like, is there something else that you want to estimate, and why is it hard?
I see. Yeah, so the thing about Levsky's method just in general is that it works well if you just have one parameter where it's good on one side and bad on the other. In this particular regression problem, I don't know that there are two parameters that I would care about. But there are other settings in which maybe there are two things I want to adapt to. So if you're doing some kind of, I don't know, bandwidth selection in multiple dimensions, then like a kernel, it goes in different directions, right? So you might care about the bandwidth in one direction versus another direction. So there might be a sigma 1 and a sigma 2. And I know that if sigma 1 is bigger than sigma 1 star, then something good happens. If sigma 2 is bigger than sigma 2 star, then something good happens. But then the question is how to do these pairwise comparisons. Because now you have a vector sigma 1, sigma 2, and you need to compare it to another one that's smaller than it.
Just following up on that. Great question. What would happen if, like, on that, suppose you insert now your interval, you had a nice circle.
I see.
So that now you can sort of projections. Each projection somehow.
Yeah, I think that would probably be okay, but I don't know of settings in which you have these sorts of guarantees, right? Because they kind of couple together the two parameters now, right? It's not like if one parameter is good or the other one, and the other one is good. It's kind of like, yeah, your surface is. Yeah. Yeah, so maybe like if the sum of the squares or something was bigger than something good would happen. Yeah.
I have a question, and one question part that. I guess implicitly you communicated throughout the talk that under the conditions in which statistical guarantees are good for non-convex settings, the algorithm, let's say a simple gradient-like algorithm, would also converge to local.
Right. Yeah. So the idea is just that as long as all the local optima are good, then I can find any one of them.
Finding them.
Oh, yeah. So I cut all of that out of the talk. But yeah, you have this sort of geometric convergence rate. So if you have some conditions, there's restricted strong convexity, and then there's also this notion of restricted smoothness. So you have upper and lower bounds on the amount of curvature. Then you can say that you actually get fast convergence to any of these local optima.
Just be clear. So point is sort of the conditions you use for getting the statistical guarantees
Yeah.
are
with one extra condition on top of that, that's good enough to get fast conversion. Yeah.
All of this has extension to the logistic regression?
Yeah, all of this, because the restricted strong convexity condition you can show holds also for logistic regression. I guess in that case, so you would want logistic regression plus a SCAD penalty. That should be totally fine. If you want to talk about a robust version of logistic regression, that's where things get a little bit more hazy. So in robust statistics, people also talk about just clipping, truncating your loss function. I don't know off the top of my head if the same analysis would work. I would have to look at exactly what this does to your loss function. But at least in terms of logistic regression plus whatever penalty you want, it should be fine.
So every time one
Mm-hmm. Yeah. Mm-hmm. So the R will be directly related to the width that you're using for your robust loss. Okay, so if your width is like 2, then your R will be like 2 times some absolute constant.
And it is not related to the L1 ball radius.
No, so the L1 ball radius is actually going to be scaling like square root of k or something. Because an L1, like if you have a sparse unit vector in L2 norm that's k sparse, then the L1 ball will need to scale like square root of k. Whereas this little r is just a constant, which is like your width of your Huber loss.
more questions.
Yeah.
Are you going to actually find a local optimum? Because then you might have to go through many saddle points, and that optimization might take a long time. Or are you satisfied with stopping at a saddle point?
Yeah, anything that satisfies the first order stationary condition will actually be close to beta star. So any method that, like some kind of gradient descent method that will find you one of these will be good.
One last question.
Mm-hmm.
In practice, potentially you're not going to reach the low saddle point
Mm-hmm.
because you're going to go through iteratively.
Mm-hmm.
So a natural approximation of having you're not going to find a gradient look like that you're finding.
I'm not sure I followed that.
Let me take it off.
Okay.
I don't want to stand in the middle of
Okay.
Well, thank you.
Thank you.
Quick announcement. So we meet again at 2 o'clock here. Now, if you need a room for discussion with a whiteboard and pen, in the second floor A wing, there are 4 rooms which are marked for workshop and then you just go there.
And we started.
And Happy New Year.